So last class we started the wing theory. So Beard-Savart law. So the original application is in electromagnetism, but we are applying that equation to our vortex filament. Okay. So strength is capital gamma induces the velocity at some arbitrary point. This equation we found. Then we simplified by expanding this modulus of dl or r cube etc. Then we applied for 4 conditions. Finite length. So here beta is here the angle is beta, here the angle is alpha. So integrate, you will get this equation. Then semi-infinite. So one end is fixed, this end is goes to infinity. So beta is 180. So substitute in this, you will get 1 plus cos theta. Then this is special case. So here the point is between these two ends, but here the arbitrary point is just opposite to that. So in this equation, instead of alpha, you have to substitute 1. Okay, so you will get 1 plus 1, 2. Sorry, 0. So cos 90 is 0. You will get gamma divided by 4 pi h. Then infinite, both sides it goes to infinity. So this becomes 180. This becomes 0. So you will get minus 1, minus 1. So totally 2. You will get gamma divided by 2 pi h. So these 4 cases we discussed. Yeah, we discussed how the CL varies for aerofoil and wing. If you take the wing, there will be a downwash, and this is how the velocities varies. So from here only the side leakage flow and the vortexes are starting. So from here onwards, the velocity is increasing, but this effect is there in the front region also. So this downwash reduces the angle of that is flow deflection and angle of attack. So CL is decreasing. So from this we got 2 basic equations. Alpha is equal to effective angle of attack and induced angle of attack. So even though if you keep your wing at 8 degree, due to the downwash, what we are getting is only 5 degree and 3 degree is lost. So okay, so the final angle of attack is effective angle of attack. So alpha is the lost in angle of attack. Then using this right angle triangle, we can relate the induced velocity and the free stream velocity. So alpha is equal to Wi divided by V infinity. These two we discussed. Okay, so this is the basic. So with that we can discuss elliptical lift distribution and general lift distribution. So this is some basics. So here I explained how the lift or circulation distribution varies for different wing platform. So initially I have taken the rectangular platform. So here red color, here also I can mention the red color. Lift distribution or circulation distribution. You know, rectangle means it will be almost constant up to certain distance. Then at the edges it will be decreasing because there will be a side leakage flow. So there will be a loss in pressure difference. So it will be almost constant. Then towards the tip it will be decreasing. Finally it will be 0. This is for rectangular wing. Okay. Then tapered wing. So in the tapered wing you see the area is decreasing. Then the lift or circulation also will be decreasing. So we are getting this blue color line. Okay. So we are getting this blue color line. So area is decreasing, lift also decreasing towards the tip. At last, there is a sudden drop in the pressure because of the side leakage flow. So this blue is for tapered. Then finally we have delta wing, that is taper ratio is 0. So here also there is a rapid decrease in area. So lift also decreasing in the same way. Okay. So this is for rectangle. This is for taper. This is for 0 degree. That is 0 taper. That is equal to the delta wing. And for remaining taper, for example, if this is 0.5, if you check for 0.7, 0.8, 0.3 and all, those lines will fall within this region. Okay. For remaining tapered wing, you will get the different profile within this region. If taper angle is value is decreasing, then the curve will shift from here to here. Okay. So here taper ratio is 1. Here taper ratio is 0. This you can approximately take 0.6 or 0.5. Okay. So remaining taper it will fall within this region. So this how lift distribution varies. Okay. And if you take rectangular wing, we are getting elliptical wing. We are getting elliptical lift distribution, the black color line. Okay. And we are going to prove this elliptical wing produces minimum induced drag. So in commercial aircraft also, if we can make the elliptical wing, we can reduce the induced drag, but manufacturing cost is very high. I think already we discussed. So instead of this elliptical wing, we are going for the tapered. You can see this black color line is the elliptical, this blue color line is for the tapered. It is almost matching. Okay, so instead of elliptical, we are going for the tapered wing so that we can reduce the manufacturing complexity. Is that clear? How lift or circulation distribution varies for different platform of the wing. Online students, any doubt? So this is
No,
for taper ratio 1. Okay, ma. This for taper ratio 0. For remaining taper ratio, it will decrease 0.8, 0.6, 0.4 like that. The curve will decrease towards this green color line. Okay. Next one. Actually, here whatever I have shown is the only one side. That is from the root to tip I have shown. Okay. If you take it for full wing, then it will be like this symmetrical pattern. Okay. So for the full wing, we will get the symmetrical pattern. Here I explain only the one side of the wing. Root to tip only explain. Okay. So this is for plain wing. So depends upon the profile, we will get symmetrical distribution. Or if it is elliptical wing, we will get elliptical distribution. This is first case. The second case, so assume I am keeping on fuselage in this wing. Okay. So we are attaching this wing in the fuselage. Now what will happen to this lift distribution? It will be same or it will vary. So what will happen if you attach the fuselage in this wing? There will be a drop in lift in that area because here you are having fuselage, right? So that will affect the lift distribution. So if there is a fuselage, it won't be exactly symmetrical. It is symmetrical about this longitudinal axis, but here there will be a drop in lift or circulation distribution. Okay. The next case, if there is a flap, deflap, you know the purpose of flap. Okay. So if you deflect the flap, it will increase the camber. Then we are getting more CL. Okay, compared to the normal wing. So here assume we have the wing and fuselage. Additionally, the flap also deflected downward. So camber is increased. So in this region, lift also will increase. So if there is no fuselage, only wing if you take, this will be the lift distribution. And if there is a fuselage attached in the wing, then this will be the lift distribution. Okay. And additionally, we have the flap also. Now what happened? In this region, we are getting more lift. And due to the fuselage, it is decreased. Again, due to the flap, it is increased. Like that, we are getting different profile. Is that clear? So wherever the flap is there, we are getting more lift. Okay, this is for flap configuration. Next one is aileron configuration. So without this aileron deflected, we will get this type of profile. Only near the fuselage it will be decreased. But here they deflected the aileron in the upward direction. So upward means it will be like a spoiler. It will disturb the flow. So lift will decrease. So because of that, what happens? The lift is decreased in this region. Then again it follows to the original profile. Here also due to the aileron, the lift is decreased. This type of profile we are getting due to the aileron deflection. Okay. And if you take the aileron for the rolling moment, or for the banking or side yaw, we know both will be deflected in different direction for rolling and side yaw movement of the aircraft. So assume one side it is lifted upward, another side it is lifted downward. So if it is lifted upward means this side more lift, downwards. Okay. So here it is deflected downwards, so more lift. Here deflected upward, so less lift. So if this deflection angle is small, then you will get this type of lift distribution. This side it is more and it is keep on decreasing. Okay. Assume just for the side banking. So we are deflecting the aileron to the different direction, upward and downward, but the deflection angle is small. So we are getting this side high, then this side low. And if you decrease this, that is deflect this to the maximum angle, so that we can roll the aircraft. Now what will happen? More deflection means more lift, and this side we will get the negative lift. Okay, so both configurations are possible. For simple banking, there will be a small deflection angle, so both may be positive. For complete rolling, if you go for the maximum deflection angle, one side positive lift, another side negative lift. Like that, we will get the asymmetrical lift distribution also. Okay. So overall, if you see, if you take the wing alone without fuselage, the profile may be like this. Okay. And if there is a fuselage, or if there is a flap deflection or aileron deflection in the same direction, then you may get this type of symmetrical pattern. Okay. So this may be happen due to the flap deflected downwards. Okay. Or here the aileron may be deflected upward. Here also it is symmetrical only about this axis. So we will get symmetrical pattern. Here and all it is symmetrical. So second option is it may be symmetrical. Then third option, it may be asymmetrical or unsymmetrical. Okay, one side more lift, one side zero, or sometimes it will be negative also if there is a rolling moment. So generally, so there will be a symmetrical pattern or there will be a asymmetrical pattern. Within this, we can include all type of aircraft maneuvering. Okay. So in this wing theory, we have two derivations. One is especially for the elliptical lift distribution. Another one is, so one is elliptical, another one is general. So using this general, we can find forces acting on this, and that is property of the elliptical, symmetrical, asymmetrical, everything. So two derivations are there. Is that clear? So we may get elliptical, symmetrical, asymmetrical. So we have two derivations. One is specifically for elliptical, another one is general, which can include all these three cases. And here the idea is, so we are going to find a circulation equation for all type of distribution. So once you know the circulation, from this we are going to find what is the downward factor on the wing. From that, what is the loss in angle of attack, then what will be the effective angle of attack, then what is the overall angle of attack, then what will be the lift and seal of the wing, then what will be the induced drag. So using potential flow, we cannot find the overall drag. Okay. But this drag is induced by this lift. So this component alone we can find it using this potential flow, thin airfoil theory, wing theory and all. Is that clear? So in this wing theory, so first I am going to find circulation equation for different profiles. From that I can find all these terms. So all these terms will be in terms of circulation. So once I know the circulation, I can find all these parameters. Like that we are going to derive it. Is that clear? So just introduction before starting the derivation. Online students? Hello?
Understood, sir.
Okay. So before going for that elliptical and general lift distribution, so we are going to derive the fundamental equation that is called Prandtl lifting line theory. Okay, based on this only we are going to derive elliptical and general. So what is this Prandtl lifting line theory? So you know, if you want to simulate flow over the wing, we have to take this hypothetical vortex filaments arrangement. Okay, horseshoe vortex. So what he did, so he wants to derive the expression for the forces acting on the left. So he simplified this configuration. So he placed all these vortex filament in the same line. Okay, see he coincides all this. Here it is spreading over the wing, right? All those vortex filaments. But for the simplification of theoretical thing, so he coincides all these vortex filaments in the single line, that is Prandtl line. Okay, and this line is called lifting line. And this theorem is called Prandtl lifting line theory. Okay, to derive the expression, so he made some simplification. So instead of spreading this vortex filaments, he superimposed all the vortex filaments in the single line. The line is called lifting line. So this theorem is called Prandtl lifting line theory. So finally, we will get the profile like this. Sorry, even the same line. Like this, he superimposed all those lines in the single line. Okay. So then he found what is the downwash induced by this semi-infinite vortices, then alpha L, alpha CL, CD, etc. and all. Okay. And here you see, so these trailing vortices produces downwash everywhere, here, everywhere. But we are interested to find the downwash velocity acting on this wing. Okay. We are not interested to find the rearward position, etc. and all. So this is the trailing edge vortices. You can see here there is a turn. That means this end is fixed. That is fine, and this end goes to infinity. Already we discussed 4 cases in the Beard-Savart law. So here you can see this is the fixed end. This goes to infinity. Then this will be like a semi-infinite vortex filament case. In the semi-infinite itself, we have 2 cases. One case we are finding velocity in the arbitrary point, which is between these 2 ends. And in the second case, we found the velocity induced in the arbitrary point, which is opposite to this fixed end. But here we are interested to find the velocity acting on the wing. That means this will be the second case. So semi-infinite vortex, which induces the velocity at the arbitrary point. That point is just opposite to the fixed end. Is that clear? So we know the formula. I think it is the gamma divided by 4 pi h. And we are going to proceed. Okay. So here, from the circulation, we are going to find induced velocity or downwash velocity, induced angle of attack, all other parameters. So first, I will start with the downwash velocity. So this is the wing. Okay. So span varies from, span we used to take it as B. Here I have taken reference point in the center. This is 0,0 point. So totally this span is B. So this side B by 2, this side B by 2. So they are taking this is positive B by 2, another side negative B by 2. Okay. So totally it is B. This point is in the center. So this side it is positive B by 2. This side it is minus B by 2. Okay. So the span varies like this. So totally it is B. Actually I said, so all those lines are coincide in the Prandtl line. I couldn't get the exact figure, so I have taken this. But assume all those lines are just coincide in this axis. Okay. So the line is called lifting line. Okay. So with that, you are going to find induced velocity. So I already told you this end is fixed, this end is goes to infinity, and we are interested to find the velocity on the wing. That is, the point is just opposite to the fixed point. So it is a special case of semi-infinite vortex filament. So this is the formula. Now we will apply this formula to this condition. So instead of taking single vortex filament, I am taking bunch of vortex filament within this region dy. Okay, so n number of vortex filaments are there. I am taking some bunch of vortex filaments in this distance dy. Okay, assume that induces the velocity at some arbitrary point on this lifting line. I am taking, so the dy is at y distance from the reference point. and this dw is at y1 distance. Is that clear? That's y1, y dy and all. Can I zoom this? Let's try. Okay. Oh, you go back again. So you can see. So the dy, it is at y distance from the 0 point, and it induces the velocity dw at some arbitrary point on the lifting line. That is at y1 distance from the 0 point. Is that clear? Y and y1 distance. Okay. Okay. So now if you write, you see the velocity is dw. Okay. And strength is, I have taken only one small distance. Okay. The complete strength is capital gamma. I have taken one small distance. Then the strength should be d gamma. Then 4 pi. Then h is difference between the fixed end and this induced arbitrary point. So here h is equal to y minus y1. Okay. So this is the general formula I have applied to this configuration. So I got dw is equal to d gamma divided by 4 pi h is equal to y minus y1. Is that clear? This is the first step. Okay. So this one we got it. So we have to find this d gamma. You see this, it is not constant. Okay, it is a curved profile. So whatever the d gamma you are getting, it will be a grading. Okay, you can see this is the curved profile. If it is constant, straight away you can take d gamma, but it is a curved profile. So what we are getting is the circulation grading. So it will be d gamma by dy. On this small distance, so whatever we are getting is the circulation grading. So it is d gamma by dy. But what we need is the d gamma. So we can write d gamma by dy into dy. That will give you the d gamma. So we have the circulation grading. Multiply this with dy so that we can get d gamma. Is that clear? So instead of this d gamma, I am writing circulation grading into dy. Okay. So this dw is induced by the small distance dy. Then if I want to find the downwards velocity induced at this point by the complete vortex filament arrangement, then simply I have to integrate it from plus b by t to minus b by 2. Okay. So for the small distance dy, it is dw. Then for the complete distance from plus b by 2 to minus b by 2, I have to simply integrate this value so that I will get w. Is that clear? So now this is the induced velocity at this arbitrary point due to the complete vortex filament arrangement. This is the final formula. Any doubt in this step? Actually, if you are coming for offline exam, so we will ask only elliptical and general F distribution. These derivation we will not ask. It is only for the understanding. Okay. Okay. So we got total downwards velocity induced at this point by the complete vortex filament. The next step. So once we know the W, we are going to find the alpha I, induced the angle of attack. So that formula already we derived. Alpha I is equal to WI divided by V infinity. Okay. Here we derived from this right angle triangle. Alpha I is equal to WI by V infinity already we derived. So once we know the WI, we can find the alpha I. Simply you have to divide this by V infinity. So we found the alpha I also. So induced velocity is found, induced angle of attack is found. Now I am going to find the effective angle of attack and total angle of attack. So to find the effective angle of attack, I am using this general CL equation. So for the aerofoil, what we have studied? the general equation is 2 pi alpha minus alpha L is equal to 0. This alpha can be 0 for symmetrical and negative for unsymmetrical aerofoils. Okay, this equation we studied. But in the wing theory, if you take, I already told you, even though it is at alpha degree, at every section if you take, what we are going to take, get is only alpha effective. Okay, so this formula, if you apply for this ring theory, then this will be alpha effective. So instead of alpha, we are writing alpha effective. This is why we are getting this equation. So generally it is 2 pi alpha minus alpha L is equal to 0. It is 0 or negative, alpha L is equal to 0. And for the wing theory, we are not getting alpha. At every section, we are getting only alpha effective. So instead of alpha, I am writing alpha effective term. So from this, by rearranging that, I can get the alpha effective. So rearrange, you'll get this term. Again, as I mentioned, so all this term, I'm going to write in terms of circulation. So I don't want this CL value, CN term. So I'm going to convert this CL in terms of gamma. So I know the relation. So L is equal to half rho V squared CL, or it is rho V gamma. Now relate these two things. We can write CL in terms of gamma. Okay, general lift equation. Then Kuta-Joukowski equation. By relating, I can find CL in terms of gamma. This term you substitute here, you will get this alpha effective term. Okay, it is in terms of velocity, chord, circulation, and alpha L is equal to 0. Okay, so now we found alpha effective also. Now we can find overall alpha, which is simply alpha effective plus alpha I. Okay, so alpha effective plus alpha I. So we found induced velocity, induced angle of attack, effective angle of attack, overall alpha. And this alpha equation is called fundamental equation of wing theory. Okay, is that clear up to this? Last bench. Then we are going to find lift CL and drag induced drag. So this is the wing. Assume this is the lift distribution. We know for the aerofoil, what is the lift equation? Rho V gamma. Using that, I can find it for the complete wing. That is simply I have to integrate this term. Okay. So for one section, I know it is rho V gamma. Then for the complete lift, simply I have to integrate it from minus b by 2 plus b by 2. Okay. So L dash dy. Then instead of L dash, I can substitute rho V gamma. So once we know the lift, I can find the CL, lift divided by half rho V square S. Okay, so substitute this L here. Then simplify, you will get this CL equation. So for the aerofoil, it is rho V gamma. Then for the lift, simply you have to integrate it. Okay. Once you know the lift, find the CL. So substitute lift, then simplify, you will get 2 divided by Vs into integral gamma dy. This is for CL. And same way we can find induced drag also. So using the Kuta-Joukowski theorem, we have written lift equation. You see, this is a free stream velocity. Due to that, we are getting lift, which is opposite to that. Okay, it is rho V gamma. The same way we can write this induced drag also. So due to this downwash, we are getting this induced drag. Again, both are 90 degree. So we can write rho Wi gamma. So for lift, it is free stream velocity into gamma. Here it is Wi into gamma. Okay. So this is how we can write the induced drag. So once you know the sectional induced drag, we can find for the complete wing simply by integrating it. Then we can substitute in this CDA equation. That's it. So this is one form of induced drag. Another form also there. So either we may use this formula, di is equal to rho Wi gamma, or this one, di is equal to L into alpha I. How they are getting this means? So previously this is the free stream direction, and if you find the lift, then lift will be perpendicular to this phi infinity. Okay, this dashed line is the lift previously. But due to the downwash, the flow got deflected downwards. Now if you find the lift, again the lift should be perpendicular to this, the deflected streamlines. Now this blue color line, inclined line is the lift. Okay, so it should be the straight line, but because of the downwash and deflected airflow, lift also got deflected. It is deflected to the angle of alpha I, so that you are getting an additional horizontal component, that is induced drag. Okay, so it should be straight because flow is straight, but flow got deflected, so lift also got deflected, so that you are getting an additional term, that is induced drag. Okay, so it is deflected to the alpha I degree. Now you can take this right angle triangle, you can find the sine alpha I dA divided by L, and we assumed alpha is very small, then alpha effective alpha I, everything will be very small. So instead of sine alpha I can write simply alpha I. So dA is equal to L into alpha I. This is the another formula. Okay, so either you can use rho W gamma or L into alpha I. Any formula you can use it. Okay, that's it. So once you know the circulation, we can find d gamma by dy, substitute everywhere. We can find induced velocity, induced angle of attack, total angle of attack, lift drag, from that CL, from that CDI, etc. That's it. That's the idea.